Okay, guys, this next section of the acid-base chapter is a little long, and so it makes sense to break it up into two parts. I'm going to focus first on this middle learning objective, where we are to rationalize the trends in acid-base strength with molecular structure. And so we'll focus on that part in this video, and then we'll save the first and third learning objectives for the next video. Recall from a previous discussion that there are strong acids and bases that completely ionize in water. Two examples are given here, and then I'll draw your attention to the table at the bottom, which contains a list of 6 strong acids and 6 strong bases. And these acids and bases should be committed to memory. You need to know that they are the strong acids and strong bases, and that any other acid that you encounter or any other base that you encounter may be regarded as a weak acid or base because it's not on this list. The leveling effect is something that occurs for strong acids and bases in water. Each of these acids appears equally strong in water due to the so-called leveling effect. That is, they are stronger acids than hydronium itself, and therefore in water they all appear to have the same strength. Now, what we're going to talk about in this video is that there are differences in acid strength based on molecular structure, and we're going to learn the rules for comparing different acids based on their molecular structure. Here is the primary rule. Okay, acid strength is essentially determined by how easily an acid loses a proton. So the more easily the acid can lose the proton, the stronger the acid it will be. And there are two primary considerations here. One is the polarity of the bond between the hydrogen atom in the acid and the atom that it's attached to. So polar bonds, that is where there's a large electronegativity difference between the proton and the atom to which it's attached, leads to enhanced acid strength. Okay, so the polarity of the hydrogen X bond makes a difference. The second criterion is the bond strength. Okay, so in order for a proton to be given away or donated easily, the bond between that proton and the atom to which it's attached must be weak. And what we find when we look at different acid bonds, that the strength of the bond decreases as the size of the parent atom increases. So if X here is a large atom, then the bond between hydrogen and X will be longer and consequently weaker. Therefore, it will be more acidic. We're going to look at two families of acids. The first family are so-called binary acids, where you have a proton directly bonded with an electronegative atom. And so different acids fall under this category. For example, hydrofluoric acid would be a binary acid. Hydrochloric acid, water itself, would be in the category of a binary acid, even though it's neutral. Hydrosulfuric acid would also be a binary acid. Here you have an atom directly connected with a hydrogen atom. And so there are two ways to compare binary acids. If the two acids line up in the same column of the periodic table, for example, HF and HCl, you use the bond length strength criterion. So for example, if you think back to your periodic trends, you know that as you go down the periodic table, the atoms get larger. So a chlorine atom is larger than a fluorine atom. And since the bond length is longer between hydrogen and chloride than it will be between hydrogen and fluoride, it will be a weaker bond, and therefore hydrogen chloride will be more acidic than hydrogen fluoride. The same thing's true if you compare here in group 16, so comparing water to hydrosulfuric acid. Sulfur is a larger atom than oxygen, therefore the hydrogen-sulfur bonds will be longer and weaker than the hydrogen-oxygen bonds. And so consequently, since there's a weaker bond between hydrogen and sulfur, it's going to be easier to give that proton away, and so hydrosulfuric acid will be a stronger acid than water. Now, when you're comparing two acids in the same row, the bond length strength criterion doesn't really matter, and that's because atoms within the same period of the periodic table have roughly the same size. That is, a fluorine atom is roughly the same size as an oxygen atom, which is roughly the same size as a nitrogen atom. So the size of the parent atom doesn't make that big of a difference in terms of acid strength. What does make a big difference within the same row of the periodic table is the polarity of the hydrogen bonded with its partner. So think about your electronegativity trends involving the periodic table. As you go across the periodic table, the electronegativity of the atoms increases. In fact, fluorine has the largest electronegativity of all of the atoms on the periodic table. And so hydrogen fluoride is a stronger acid than water because the HF bond is more polar, and therefore the hydrogen is more susceptible to being donated away than it is in water. The same thing's true when you compare water to ammonia. The OH bond is much more polar than a nitrogen-hydrogen bond, and so by comparison, or at least relatively speaking, the hydrogen in water can be given away more easily than the hydrogen in ammonia. And in fact, ammonia, as we've learned already, is a weak base. It's not acidic at all. So the second family of acids that we'll talk about are oxoacids or oxyacids. Those are synonyms for one another. An oxoacid has this sort of complicated form written here. It's a lot easier just to look at the picture. You have some central parent atom, usually an electronegative atom, like chlorine or bromine or sulfur or something like that. And then surrounding the electronegative atom are a different number of oxygen atoms. In this case, we're showing one oxygen atom, but there could be up to a total of 4 oxygen atoms around that electronegative atom. And then the acidic proton is attached to the oxygen atom. Different acids that we've encountered in the past have that form. For example, sulfuric acid has that form, as does nitric acid. We also have nitrous acid and sulfurous acid that also meet that form. And so what we'll be comparing is different acids with the same electronegative atom that have different numbers of oxygen atoms. And so that's this second rule here. Okay, the strength of the acid increases with the number of oxygen atoms around the parent atom. And so I have a example on paper that I wanted to show you. So if we look here I've written a family of oxoacids. So this is perchloric acid, this is chloric acid, chlorous acid, and hypochlorous acid. And they all have this same structure, except for that perchloric acid will have a total of 4 oxygen atoms around the chlorine, whereas, say, hypochlorous acid only has 1 oxygen around the center atom. And so the rule is, as you increase the number of oxygen atoms in the oxoacid, the bond between oxygen and hydrogen becomes more and more polar, and therefore it becomes easier to donate that proton away. So of this list, perchloric acid is the strongest acid, and hypochlorous acid is the weakest acid. In fact, perchloric acid is the strongest acid that we'll encounter in the lecture. The second rule, or first rule, depending on how you look at it, is this one here. This would be for comparing acids that have the same number of oxygen atoms, but different central atoms. So for example, if you were to compare nitric acid to sulfurous acid, okay, they have an equal number of oxygen atoms, but they have different center atoms. And so how would you choose which of these two acids is the strongest? Well, you would use this rule here, the fact that the acidity of the acid increases with the electronegativity of the center atom. Okay, and so in this case, the nitric acid, nitrogen is more electronegative than sulfur, and so nitric acid is going to be a much stronger acid than sulfurous acid. Notice that in the oxoacids, we make no mention of the bond length strength criteria. And that's because for all oxoacids, the hydrogen atom is not bonded directly to the electronegative atom. It's always attached to an oxygen atom. And so there, the bond length between oxygen and hydrogen for different oxoacids is always about the same. And so bond length, bond strength is the same for basically every oxoacid. What makes the difference here is the electronegativity, the polarity of the oxygen-hydrogen bond. We also have a rule for polyprotic acids, and so these are acids that have more than one acidic proton. For example, sulfuric acid has 2 acidic protons, and you can imagine there are 2 ionization reactions for it. So in this first ionization reaction, 1 proton is donated away, giving us the hydrogen sulfate ion. This acetic anion can also donate a proton away. And I have a little typo here. This should be SO4, 2 minus, the sulfate ion. The question is which of these two acids is stronger? Is the sulfuric acid stronger, or is the hydrogen sulfate ion a stronger acid? And essentially, the negative charge on the hydrogen sulfate ion attracts protons towards it, so it makes it harder to donate away that proton compared to sulfuric acid. So among these two, sulfuric acid would be the stronger of the two. In fact, sulfuric acid is a very strong acid, where hydrogen sulfate would be relatively speaking quite weak. So this example problem illustrates what you need to be able to do on the assessments. Essentially, what you're going to be given are different combinations of acids, and you have to compare their relative strengths. So, for example, you might be given a list of 5 acids, and the question will be, which of the following is the strongest acid? Or which of the following is the weakest acid? Or here's a list of acids, rank them in order of increasing strength. That kind of thing. So here's a set of 5 pairs of acids, and we're to determine which of the ones in the pair is the strongest. So here in this first example, we're trying to compare ammonia to phosphorus trihydride, and they want to know which of these is going to be the stronger acid. What you have to do is you have to use your periodic table, and you have to find the parent. For these binary acids, you have to find the parent atom in the periodic table. And so we see that nitrogen and phosphorus both line up in the same column of the periodic table. And the rule for binary acids that are in the same column of the periodic table is that as you go down the periodic table, the parent atom gets bigger, and therefore the hydrogen atom, the bond length of the hydrogen to the parent atom gets longer and therefore weaker. So the bond between hydrogen and phosphorus is going to be longer and weaker than the bond between hydrogen and nitrogen. Consequently, it will be easier to donate away that proton for the phosphorus trihydride compared to the nitrogen, compared to the ammonia. So the stronger acid is the phosphorus trihydride in this case. In part B here, we're comparing hydroiodic acid to hydrotelluric acid, okay, and we see that those are binary acids that are in the same row of the periodic table. And so it's not the bond length strength criterion that we want to use here, because an iodine atom is roughly the same size as a tellurium atom. What we need to do is use the bond polarity criterion. Okay, and so we'll use the fact that iodine is going to have a larger electronegativity difference with hydrogen compared to tellurium. So because iodine is more electronegative than tellurium, we would expect the HI bond to be more polar, and therefore it will be easier to donate the proton away in hydroiodic acid. So hydroiodic acid is the stronger of the two acids in this example. In part C, we have the hydrogen sulfite ion compared to sulfurous acid, and so we'll recognize these two as being members of a polyprotic acid family. And the rule there is that the neutral species is going to be more acidic than the anion. So the sulfurous acid is going to be a stronger acid than the hydrogen sulfite ion. In part D, we have an oxyacid. Okay, we see that the center atom is arsenic. Okay, and the difference between the two acids is the number of oxygen atoms. And the rule there is that the more oxygen atoms you have, the greater the polarity between the hydrogen and oxygen atoms, and therefore the more easily the protons can be donated away. So between arsenic acid and arsenous acid, the arsenic acid is the stronger of the two. In part E, we have two acid anions. They're oxoacid anions, and we see that they have the same number of oxygen atoms. They are charged, but they have the same charge. They're both -1. So it's not the number of oxygen atoms, it's not the charge of the species that makes a difference. It's going to be the center atom. And we find that sulfur and selenium here, they are in the same column of the periodic table. Now it may be tempting to use the bond length strength criterion as justification for which acid is stronger or weaker, but that would be incorrect in this case, because these are oxoacids, and the hydrogen is not directly attached to the center atom. In fact, it's attached to an oxygen atom. So an oxygen-hydrogen bond length in the hydrogen selenate ion is going to be roughly the same length and strength as the hydrogen-oxygen bond in the hydrogen sulfate ion. So we don't want to be using the bond length strength criterion to make our judgment. We want to use electronegativity and bond polarity. And so we want to think about which of these atoms is going to be more electronegative. In fact, it's going to be the sulfur atom that's more electronegative than selenium. Therefore, the hydrogen-oxygen bond in hydrogen sulfate will be more polar, and therefore it will be easier to donate away the proton in the hydrogen sulfate ion. So between the two of them, the stronger one is the hydrogen sulfate. I have one more concept for this video, and that goes back to the idea of conjugate acid-base pairs. And we have a strength rule involving conjugate acid-base pairs. Acids that are very strong, for example, perchloric acid is the strongest acid here on the list. Strong acids have weak conjugate bases. So the perchlorate ion is a very weak base, because the perchloric acid is a very strong acid. Hydrogen chloride is a very strong acid, and consequently the chloride ion is very weak. Same thing for nitric acid. Nitric acid is very strong, but nitrate ion is a very weak base. The opposite is true. If you have a weak base, for example, let's choose acetic acid. That's a good weak acid. Relatively speaking, the acetate ion would be fairly strong. Okay, so acetic acid is weak. The acetate ion is a fairly strong base. Okay, and so we want to keep this, we're going to use this rule in a later video, particularly when we look at hydrolysis involving ions. Okay, we'll need to make use of this rule. Okay, so that should be it for this one. We'll start here on the next video.